Hello, this is Xianghe Dai from University of Bradford, UK. Today, I will present our research on experimental study of composite cellular beam system using demountable shear collector. Okay, the presentation will cover a brief introduction, experimental program, and conclusions. Okay, as we know, currently steel concrete composite beam systems are extensively used in construction practice. They may effectively use both steel and concrete material tensile and compressive strength via shear collectors. Using steel cellular beam may reduce structure self-weight, increase beam span, increase beam depth, stiffness, make service convenience. However, traditional composite beam using weighted shear collectors can't be dismantled easily and can't be reused after design life. So demountable shear composite beam system using demountable shear collector will be welcomed into easy dismantlement and member reuse in the future. The main objectives of our research project are to investigate the ability of the composite beam to develop its plastic bending resistance and stiffness with a lower degree of bolted shear collection, the development of local composite action at the opening to resist one-linear bending, the effect of unpropped construction on the longitudinal shear collector forces, the effect of partial shear collection and regular opening on the additional deflection of composite beams, the performance of shear collection with cast-in edge tree placed in between the pairs of boards along the center line of the beam in the longitudinal axis. Demountable ability of the composite cellular beam after first use. Okay, here we'll show you some specimen feature. Composite beam system 11.2 meter length, and the slab is 2.8 meter wide, slab depth 150 millimeters. Steel cellular beam depth 427 millimeter. We use a universe beam for the cellular beam top T, and we use the universe collar for the cellular beam bottom T section. The bottom flange area to the top flange area ratio is 2.4. Shear collectors we used is G grade 8.8 and 20 both. Close to the end of the composite beam, the specimen is 300, and close to the center of the beam, the specimen is 600 in a staggered pattern. The collector was embedded within the concrete slab 120 millimeter and tightened to a torque of 120 Newton meter. Slab concrete grade C30-37, and the measured strength is about 40 Newton per millimeter square. 19 shear collector between the end and the force loading point, and the degree of shear collection was 38%. Okay, this draw show you the dimension of the cellular beam, and all the shear collector, the cross section of the cellular beam. Here show you the shear collector position. Okay, the arrangement. You can see this is paired close to the end and staggered close to the center, and the spacing is 600. Okay, this photo show you the reinforcement mesh inside the concrete slab, but also show you the shear collector position and the edge train at the midline. Okay, this photo show you the specimen test setup. We used 3 jackers, and also we use the spring beam system to apply the load to the top of the composite system. Okay, the loading applied at 8 points along the beam length to simulate the effects of uniformly distributed load. 4 loading cycles performed. The first one up to 2 kilonewton per meter square. The second up to 5 kilonewton per meter square. This is the working load. And also the third one, 10 kilonewton per meter square. The fourth cycle up to failure load. Okay, this graph shows you the vertical deflection of the cellular beam after concreting. You can see the maximum deflection at the meter span is about 30 millimeter. Okay, the graph and this table show you the relationship of the load to the meter span deflection. So you can clearly see 4 cycles here, and also the load up to 60% of the maximum load looks like straight here. So this is a linear, close to linear. Okay, and this graph show you the relationship of the load and the slip. These 2 graphs show you the slip at the end between the slab and the steel beam. These 2 graphs show you the slip at the second shear collector from the edge, from the end of the beam system. Okay, this graph show you the relationship of the load and the strain at the meter span at the bottom flange of the cellular beam. You can clearly see the yield here. Okay, and this graph and the figure show you the strain at around the shears. So you can see from this point and this point, you can see the yield. This is over 2000 mu. Okay, and this graph show you the deformation after the test. This is to say when the specimen reach the failure load, you can see the deflection, deflected beams. Okay, here, this is the demotability checker. After the initial set of tester, the beam was cut. and take apart one piece at a time and then reassemble it. Demonstrated the ease with which this type of beam can be deconstructed using demountable shear collectors. The edge tree and the mid B-tree shear collector proved to be effective in enabling this demountability. Okay, and conclusion. The failure load is 24.3 kilonewton per meter square, which was very close to the predicted load based on the characteristics shear resistance of the shear collector. And the test failure model was pure bending by tension yielding of the bolt T at a total moment of 1,207 kilonewton meter. The shear force was slightly higher than the Weber post shear resistance, but which didn't fail despite the higher strain recorded. The bolted shear collector exhibited a higher deformation capacity, undergoing 8.1 millimeter slip prior to failure, demonstrating their capacity of reach their longitude shear resistance. The displacement at a working load of 5 kilonewton per meter square was 15.6 millimeter, which agreed well with the design deflection based on the measured stiffness of the bolted shear collector from push-off tester. The deflection of failure was 135.5 millimeter, which was achieved in a ductile manner with no loss of shear connection. The load deflection relationship was linear up to about 60% of the failure load. The beam was easily deconstructed and reconstructed at the end of the test, demonstrating the reusability of this type of component. The testers demonstrated that a long-span composite beam can be designed plastically for a lower degree of shear connection using this new type of demountable shear collector, and also that lock composite action could be achieved at the opening to resist Warrenier bending. Okay, thanks to the funding provided from the European Commission. Also thanks to the joint project partner, thanks to the technical team at the University of Bradford. Thank you for attendance.